We are starting off with the plenary session 4. I request Professor Mahavir Bhattacharya, past President of Indian Geotechnical Society and the Chair of this session, to be on stage. I also invite the co-chair of this session, Professor Murali Krishna from IIT Tirupati and National Executive Committee member of the Indian Geotechnical Society. In this plenary session, we have 3 keynote lectures, 3 announcements and 4 corporate presentations. And as chair, we have Professor Mahavir Bhattacharya, past president of IGS, and as co-chair, we have Professor Murali Krishna from IIT Tirupati and National Executive Committee member of IGS. Over to you, sirs, starting off with the proceedings. Thank you.
Because I cannot get an instrument back to us. So I can put it on hold. Don't worry.
Ladies and gentlemen, as the screen is getting ready, let's get some understanding of the topics that will be presented. We have speakers on topics: precast slurry walls and plunged concrete columns, an alternative for the top-down system. This will be presented by Professor Walter, the Vice President of International Society for Soil Mechanics and Geotechnical Engineering. Following that, we will have keynote lecture 9 by Professor Buddhima Ikaratna from University of Technology, Sydney, and he will talk on advanced geotechnical solutions for sustainable transportation infrastructure using waste materials. And we have yet another keynote lecture by Professor Leslie, Director of Soil Mechanics Laboratory, Swiss Federal Institute of Technology, Switzerland, on the topic biocementation, advancing sustainable soil stabilization in geotechnics. We will also hear to Professor Zhang as well as Engineer Srilal Sahabattu and Engineer Daniel Polo on announcements they have to make. We are thankful to all of the sponsors for making this conference happen.
I request the organizers to send the audience from the outside. Organizers, please send some volunteers to send the delegates inside. Before we invite the speaker on the dais.
Vice President, ISSMB North America, and founder and CEO of Biotech Mexico. More details are visible on the screen. He will enlighten us on the theme of precast slurry walls and 12 concrete columns and alternative for the top-down system. Now I request our chief speaker to kindly go ahead. Time available is 25 minutes.
Thank you, Mr. Chairman. Shall we start or shall we wait for the audience?
Then we can get water.
Specialized Chinese cafes and whatnot. Yeah. So they may be different type of.
It's coming. Yes. Louis Hello. Ask the people to come.
Please put the first speaker details.
To kindly start your lecture, please.
Thank you, Mr. Chairman.
Go ahead.
Thank you. Then, presentation. Okay, thank you. Today I would like to share with you a different approach and procedure that is not so popular worldwide. I have found out that there's a lack of understanding between the contractors and the consultants. And it's interesting because the contractors do not know much about the technique, and the consultants do not know much about construction procedures. So there's a lack of communication over there. I think we can put a step forward with this presentation. I come from Mexico. Mexico City is the red dot list. Manage this. Here it is, Mexico City, the center of the country. At the beginning of the 1500s, Mexico City was just like this lake area, surrounded by beautiful lakes. There's this structure that you like this south lake, water line
this one,
over
just-
here.
just now,
it was connected
everything
by
is
some
stopped.
roads to mainland. The center of the city was here, and the population was around here. It was 100,000 people. Nowadays, we have 22 million people at the early 20th century, and the city has grown largely, and we have some geotechnical challenges that I will address. Geographically speaking, we have divided the city in 3 zones. First, where the lake used to be, the blue area, we call it the lake zone, that reason, but the lakes are dry now. And there is a hill zone around the lakes with tuff here, basalt, and on the side rock over here. And in between there's a transition zone. Well, problem with our lake zone is that there is a very soft and compressible soil. We have up to 45 meters of very soft clay with water content up to 400. In some areas even more. The enrichment depth is between 3 and 5 pounds per square meter. That the consequence is that low bearing capacity of foundations, and it's difficult to excavate over there. Moreover, we have regional subsidies due to pumping of water for the population consumption. In some areas, the subsidies is up to 40 centimeters per year. Professor Vladimir Radna knows this very well, and he will talk about that later. That consequences, we have total differential settlements all over the place with serious structural consequences. And to end with, we have a seismic area with this kind of soil period and amplification phenomena because the soft clay presence that conducts to high seismic loads and bad behavior, especially with friction pads. And while the city is growing, here is a skyline of some projects that are already done or under construction, up to 270 meters, and the client's demands are these ones. They need higher buildings, deeper excavations for basements and parking spaces, more tight spaces because the city is all crowded, and more speedy construction schedules. Everybody wants it fast and cheap and with good quality. In excavations, that's the topic for today, the records in the soft soil is 40 meters, in sand and clay 40 meters, and silty sand 50 meters. There are some examples of those kind of excavations, which are a challenge these days. This video, courtesy of Solar Panchmashi Corporation, shows you this kind of excavations. This is 40 meters depth. It is supported by the slurry wall, and the shoring system are post-tension anchors. You can see it's a challenge both in geotechnical and logistic engineering. So we have to manage to interact between contractors and consultants to solve this kind of construction procedures. Now, I have listed some of the most popular retaining wall systems over here, diaphragm walls, both casting place or precast sheet piles from different materials, piles, second engine separated shotgrid or others like solely revised lining, soil mixing and geoportic walls. On the other column, we have the shoring systems, anchors, suspension, struts with 5-inch beam concrete, verse slope or top-down system. The beauty of this thing is that you can choose any of the systems on the left and you can use with any of the systems on the right, depending on the soil conditions, water table presence or not, and other things. So the same goes for all the other systems. You can choose whatever you want, depending again on the project and the soil conditions. Well, just a brief review of the top-down system, which I will talk with the case history later, is this. Initially, you build the slurry wall on the perimeter, you build the piles in here, cross shaft mostly, and you have launch columns in there. So you're standing like this. If you are under the water table, you also install pumping wells to lower the water table. Afterwards, you construct the ground level slab leaving a separate void in here to access for an excavation. Then you excavate under the slab, which is supported by the slurry walls and the piles, and you can excavate the first level of basement. At the same time, you can go up with the structure. That's how it's called the top down, because you go top and then you can go down. It saves a lot of time in the construction schedule overall. You are doing this simultaneously two activities. And you can build the intermediate slab, keeping the same void that coincides on side with the top. Now, this slab is a shoring system itself. It saves money to the client because you are not using some material that will be disposed later, like a strut or anchors. This slab is the final slab construction. You continue this process until you reach to the end with the bottom slab, and then these columns usually are completed with more concrete and reinforced steel, and then you can also build the car ramps or the elevators, stairs. Some issues are the launching columns that you can put in several ways. Usually there are small metallic profiles like beams or boxes or pipes, and then you are covering afterwards the excavation with more concrete and steel. The problem with these columns is that it should be perfect because they are the final columns of the project, so they are difficult to put. Also, you want to put some extra shear devices like these Nelson bolts that go inside of the concrete of the pile to increase the shear resistance of the column. Well, I will present the case history with a different procedure than the typical one that I have shown you. This building that is over here, it's around 25 or 30 stories, I can remember. And it's located in the lake zone in Mexico City. It's on right here within the orange perimeter, and on one side we have a very busy cycling road, plus a bus dedicated lane. Over here, another 6-lane road, plus a subway station that is very close to the project, sensitive houses around here, and a hospital to end with. So the project is very complicated from the construction point of view. There are some pictures of the exterior of the north boundary, where you can see how close the subway facilities are. You can see some cracks in here that is not, the previous building was not behaving properly. In the inner side, the client had already demolished the basement, but not the walls and the bottom slab of the previous project. Now, we began demolishing the previous wall of the basement within the solder piles, some shotcrete like here. And we protected the sensitive houses with some wire mesh and hand-placed mortar to avoid the damaging these structures. That's it. Now that we are in this place, we have this general profile. We have 2.5 basements. The piles are around here at 30.5 meters, and the excavation level maximum will be 7.5 meters here, with a cistern around here. The soil, I will talk a little bit about it. The soil, you can see the CPT profile here, where you can see that there's a clay crust, and then very soft clay all the way to the cistern wall. Continuously, soft clay continues, and the piles are at 30 meters depth, where you can find some more resistant soil. I will not go into details of this profile, but we can talk later if you want. Now, the project was solved with a perimeter slurry wall, and the architect didn't want columns around here, so we integrated the walls as barracks in this boundary, and also within the elevator stair area. So these barracks are at the same depth as the piles, 30 meters depth. And the rest of also these parts, and the rest of the wall is only 11 to 15 meters depth. The general procedure for the precast walls was to excavate understory mud and use either bentonite mud or ordinary mud. I think in this one we use ordinary mud because of disposal. It's very difficult. You place then the wall inside the excavation, leaving some space in the sides and in the bottom. And that space is now filled with a self-hardening slurry that is made out of cement, bentonite, and water. The wall is hanged from the guide wall with some special device, and when the self-hardening slurry gets some resistance, then you can release the wall and it's sustained by the lateral friction. Viewing the cut of the walls along the boundary, the foundation wall in one piece, it's like this, but the bars are made in 3 pieces because they're too large, 30 meters long. And remember, they are precast. Well, this is the detail of the typical precast wall, 3.5 meters width, 40 meters thickness, and the bars are smaller, 2 meters, because they are made in 3 pieces. This is a view of manufacturing of the pressurized walls. A pressurized element has the benefit that you have higher resistant bending moment, so you can excavate larger portions with safety. Also, they have some voids in here to diminish the weight of the wall, so you can handle it with a small crane. Transportation to the job site, the trucks. And this is the limit for the size of the wall, the transportation, because you cannot do it very wide, because the roads will not allow it. Afterwards, there's a procedure for excavating. You excavate the story walls always in 3 parts, part A, part B, and part C. And please note that part C is the last one. That's where you adjust the width of excavation of the trench. And you want to do it that way because you have soil on one side and on the other part B, same thing on part B, and part C, it doesn't matter because you got that here. But you have a square excavation between parts A and B. If you excavate it continuously, then you will have like a curved trench that you don't want because your walls are square. Also, the preferred system will be to excavate one of the trenches here and then move the machine to the other, while the crane that will mount the walls will be visible here. Then you go like zigzag rows that you can see over here. So there's a lifting and placement of the precast wall. First here is the wrap to do the trench. Here are the walls. This, as I remember, is a 120 long crane. There are some pipes that are left in here. The red pipes are for the devices that we will use later during the excavation of the core. Also, we left some pipes for gravity of the self-hardening slurry I have explained before. And then you put the walls hanging from these devices onto the guide wall. All the dotted lines here are filled with poly slurry, and then it is grounded, and then is filled like in here, the brown area, to make it self-sustaining after the hardening is cured. Note please that there is no contact at the bottom or the sides. That's because hanging from these devices, the wall itself plumps. So it has a very good quality, geometric position. Now, talking about the self-hardening slurry, there's charts like this, where you have here weight, percentage in water, weight percentage in cement and bentonite. This is the whole area where we can manage our slurry, but we want to do it in here, in the yellow spot. Across, there are lines which show the resistance of 28 confined and compressive strength, and we are using the 1 kilograms per square centimeter in strength. It's very low, but it's higher, much more higher than the clay. Also, there is the connection between the walls, the vertical shear joint. Here it is, with additional reinforcement that is constructed after the excavation with the framework around here, and it's very tight. For barrels, we also use high walls like this one. You can see it's a very heavy piece with small holes in here to hang it from the high wall until we put next piece above. And there's some grout in here, like a high resistance mortar. And with these windows, we put a nut and a bolt. It is tightened so you can have a TV wall. Now, that's the wall, but we also have piles for the load of the building, the foundation. Piles 120 up to 140 centimeters diameter with this distribution. And for the top-down procedure, we need punch holes. So also drilling under the story mat, the reinforcement steel placement, then the concrete with traffic pipe, and you want to put the column with the fresh concrete in here. And there's a metallic element here with shear connections for receiving the column. And afterwards we fill the void on the top with regular to avoid accidents in the job site. So here it is the guide wall, the columns that are transported to this job site, and here the connections with additional shear resistance for the embedment of large column. Now in the building city code, we have the imperative necessity. It's mandatory to do piling integrity testing. So for this case, we left some PVC pipes for doing the cross-hole piling integrity testing. You know that you place several pipes around and you do the cross-hole testing of the possible combinations, so you can get a full image of how is it work. This is photos of people doing the cross-hole testing through the pipes, and typical results, and the qualification of the piling is good for tracking. Now, for the excavation process, we started doing a capping beam over the story wall and the ground level slab with the void under excavation. Then we have made a double level excavation because the stress the wall allow us to do that. In between, here it's the cistern. So next step will be to build this slab and excavate the cistern, the bottom slab for the cistern, and the intermediate slab for the parking basement. And these are the holes that were left for the excavation. This is the access ramp from the street. This is the part of the elevator and stair box. Here you can see this is a very heavy avenue. The subway station is around here, practically close to the building. And well, this is the building process, the top-down system. These are photographs, wall terminated, and you can see that well, it has excellent, I will say, appearance in contrast with the custom story wall that also always has some effects on the surface. This is the finished building, and we placed during the excavation process 5 kilometers in this area. 2 are near the subway, one in the BC Avenue, one in the sensitive houses, other in the hospital boundary. And well, the early measurements of the kilometer, and hopefully it will behave very well. So to end, final comments. Presented the use of precast prestressed walls as an alternative to casting place walls for case history proceeding with high compressible and low shear strength. Also, the alternative of precast launch columns as an alternative to steel or combined columns was presented, which was very innovative order. And it is highly recommended to perform a continuous monitoring to assure the proper behavior of the excavation. And with that, I finish. Thank you.
Thank you very much for saying this today. Sir, please.
Thank you, sir.
Please.
I request Professor Mohamed Nasaria to present the memento to Professor Walter Kalinga, the Vice President of North America International Society for Soil Mechanics and Geotechnical Engineering. Thank you, sirs. Now I invite Professor Frank Sam from Tongji University to make an announcement before we move on to the next sessions. Professor Frank Sam from Tongji University.
Just a short introduction to our societies to run for round 4 to 2006 ICSMG. I'll take your 3 minutes. This is the picture of Shanghai Metropolitan. And we have a lot of civil engineering construction site, China, as you know. Shanghai is the largest city in China, and we have a lot of facilities under construction or have already completed. For instance, the high-speed rail networks in China is over 50,000 kilometers north, and many metropolitans, and also the long bridge connecting the Zhuhai, Macau, and Hong Kong. And also many, urban development, the city construction planning, you can see something very attractive. And also, Shanghai, we also have big, metros, Shanghai metros over 830 kilometers, another 200 kilometers under construction. And also big, trans-ocean road around Shanghai and the port of Donghai. And this is the Shanghai Towers, built 10 years ago. A small view. There is 26 million people in Shanghai. They have two huge airports, which is the first. More than 100 million people each year, and the world's largest port. And also the exhibition rooms and some scientific parks. And many traditional buildings combined with modern city, and also Chinese traditional art. And welcome to Shanghai. See you 2030. build even halls which can host 4,000 people and with exhibition space of 25,000 square kilometers in the city of Shanghai. And with the transportation from all over the world to the Shanghai, to big airport, and also we have 16-inch port open to outside world with 10 days stay of foreigner in China for free of visa. And we also have a lot of experience in hosting many important conferences. Here, major I introduced the Shanghai 2006 start. Now, last year, the president of ISNG also visited us. There is 5 have already completed. The last one, the conference is from there are 800 participants from all over the world. Yes, just like this way. Thank you very much for your special and welcome.
Thank you, Professor Sam. I now invite Engineer K.L. Srilal Sambandhu, the President of Sri Lankan Geotechnical Society, to make an announcement.
The video.
Join us at the International Conference on Geotechnical Engineering, ICGE 2026, to be held in vibrant and welcoming city of Colombo, Sri Lanka. ICGE has always stood as hallmark event under the umbrella of ISSGE, bringing together professionals from our diverse and dynamic region. It is more than forum, a presenting technical papers. It is a confluence of minds, a platform of collaboration and innovation, and a celebration of the geotechnical professional's vital role in shaping a resilient and substantial world. Conference theme: Resilient Geotechnics and Sustainable Future. This theme has been carefully chosen to reflect the present realities of our time. Across Asia and Pacific, we are witnessing unprecedented infrastructure growth driven by urbanization, technological transformation, and the urgent call to adapt climate change. As we navigate these changes, geotechnical engineers stand at the forefront, designing systems that are not only technically sound, but also resilient, adaptive, and sustainable. Theme areas: our conference will encompass a broad spectrum of contemporary topics, including geotechnical modeling, design of earthquake and dynamic loads, environmental geotechnics, foundation and ground improvement, geotechnics of natural disaster and resilience, sustainable geotechnical practices for infrastructure development, use of AI, robotics, deep learning, and machine learning in geotechnical engineering, energy geotechnics, offshore and offshore geotechnics, geotechnical risk assessment and management, engineering geology, rock engineering, and tunneling, advanced site investigation and characterization, transportation geotechnics, and problematic soil, geosynthesis, deep excavation, and case studies. These areas collectively improve our shared vision, engineering for sustainable and secure future. ICGE 2026 will serve as a dynamic platform to share practical experience and research findings, to learn from success and challenges, and to build networks and transcend national boundaries. The conference will feature technical sessions, policy dialogues, and interactive forums on critical topics such as climate excellence, infrastructure, smart and sustainable cities, water resource management, financial resilience, infrastructure, ethical responsibilities of engineers in an evolving world. But friends, ISSG 2026 in Colombo will be more than a professional gathering, it will be an experience. Sri Lanka has had the privilege of hosting ICT before, most memorably 2015 and again 2021, when we launched to a virtual platform during the global pandemic. Each edition left delegates enriched by dialogue, strengthened by collaboration, and deeply touched by Sri Lankan warmth and hospitality. In 2026, we aspire to build that legacy, to offer an event that is technically enriching, culturally vibrant, and personally memorable. Sri Lanka, the pearl of Indian Ocean. Our island is often called the pearl of Indian Ocean, and rightfully so. From sunset beaches and misty islands, and from ancient engineering marvels to modern urban landscapes, Sri Lanka is a living testament to the fusion of nature, heritage, and innovation. Our ancient cities, our Rajut and Purnarva, stand as silent witness to 2,500 years old civilization that mastered the art of hydraulic engineering, creating reservoirs and canals that will sustain communities today. The rock coaster of Srinagar, which is water gardens and artistic splendors, reflect timeless harmony between engineering and aesthetic version. During ICT 2026, we will organize technical tours to major nation projects, including Central Expressway, along Port City, and other transport infrastructure developments. Dear colleagues and friends, ICT 2006 will be placed the idea of meet opportunity, the innovation meet tradition, and where collaboration was an enduring participation. We eagerly look forward to welcoming you to Sri Lanka. I may you live long and prosper. Thank you.
Thank you, Engineer Sahabu. And now we have the corporate presentation slow. Without the help of the sponsors, Geotech Asia wouldn't have been a reality. I invite Mr. N.K. Nanda, Managing Director, India and Nepal, from McAfee for making the presentation. McAfee is the diamond sponsor of Geotech Asia 2025. We request you to kindly stick on to the time. If you could finish by 5 minutes, it would have been good. Thank you.
Thank you. Good morning. I was told 10 minutes and now there is a challenging task of 5 minutes, so that's interesting. Thank you. First of all, a big thanks to the organizing committee for organizing this event here in India. And it's a privilege to be part of this event and get associated with that. So thank you. Thanks a lot, and I welcome all the dignitaries on behalf of McAfee. I also welcome our McAfee team, including Mr. Vikramjit Roy, India Southeast Asia Pacific Regional Head, and our McAfee team, named Dr. Ratnakar, Mini, and them are joining me. Thank you. So the theme is for McAfee, is nurturing the world of tomorrow. I want to briefly touch upon what does this mean to us and what does this mean for all of us. So this is at the core of whatever we do. This is what drives us, nurturing the world of tomorrow. Now, what does this mean? This essentially means that we will do everything which will help us lead to a better, a greener, and a more sustainable tomorrow. This is a pretty wide statement. Over the next few slides, I want to touch a few aspects of this theme with which we are working here in McAfee. Well, I just kept a slide who we are. I'm sure many of us know still, for over 140 years, we are the leading international provider of advanced solutions to the civil, geotechnical, and the environmental construction market. So the few use cases of some of our solutions, including retaining walls, to hydraulic walls, to compound systems, and soil reinforcement solutions. I thought of putting few application areas just to highlight what we are doing. But briefly touching upon, we are providing solutions around retaining walls, falling reinforcement, masonry reinforcement, erosion control, soil stabilization in pavements, hydraulic works, landscape architecture, tunneling, noise barriers, environmental watering and landfills, and so on and so forth. Quickly, our daily activities are at a glance. Maybe I will touch 2-3 points. One of the themes is fostering innovation. There is a continuous improvement in McAfee through engineering, test campaigns, and benchmarking, including the product performance evaluation, which we do for each and every product which goes as a part of our solutions. The second point is the responsible design introduction, which necessarily means how we are using our sustainable material management and our focus on reuse and recycle of different materials that we use. The third pillar is clean energy adoption. Wherever we provide solutions, we try to put in elements of vegetation. Fourth is the integration into the natural environment, which enhance the biodiversity in the solution that we provide. The safety of people and assets, because a lot of our solutions are around preventing disaster risks and also preserving our cultural heritage, necessarily protecting the assets and the people. And involvement of local communities, which we will touch on this in one of the examples. I'll not get into this, but this is just to highlight that we are aligned towards the 17 Sustainable Development Goals as devised by UN. There are 8 themes which we are closely working on. Maybe if I will touch upon 3-4 examples, if time permits more, but maybe 3-4. So this is one example of where we promote the reducing the material and avoiding the waste. So this is an example of the Renomac mattress, Reno mattress plus textile. And if you see that the conventional solution of hydraulic bank protection by the additional solution as compared to the current design, vis-a-vis the McAfee design, you see there can bring material savings of more than 70%. This necessarily means less CO2 emissions, less truck movements, and more reduction in the environmental footprint within the river bank protections. Just to extend the same example, our pre-filled solutions like Renomac and Cubimac, which goes under water installation, which means the underwater installations of the gapings and the mattresses, they considerably reduce the material waste, right? And this is what we have supply cases here in India and globally both. The use of the materials is again very core to all the solutions that to a lot of the solutions that we provide. We have a wide range of geogrids through which we maximize the opportunity to reuse the site-borne materials as backfill.
Mr. Pathak, can you please conclude in 1-2 minutes?
Okay. Maybe I will quickly touch upon this. This is the life cycle transparency. A lot of our products are environmental product declaration certified, EPD certified, which necessarily means they have gone through a life cycle to understand how it can minimize the impact on the environment. Vegetation I touched upon. Maybe I'll just touch upon this in my presentation. So this is basically the risk mitigation and disaster prevention. This is how we are able to minimize the risk of disaster and protect the people and assets. This is an example of a temple, Saptashringi in Maharashtra, where during the plague more than 3,000 people throng the temple every day. Through our multiple protection measures, we have been able to protect the temple, adjoining infrastructure assets, and of course, protect the movement of the people and protecting the diversity also as well. This is a photograph which is taken from 200 meters from the roads level, and there are some multiple such kind of works that we have done both in India and globally. Well, since I have limited time, maybe I'll just touch upon what this necessarily means for McAfee, that we are committed to use the alternate materials which will reduce the carbon footprint. Use of geosynthetics is proven, and we want to bring in more solutions using geosynthetics. We, for sure, in all of our solutions, we use the locally available materials rather than necessarily using concrete, etc. As we speak, we are constantly innovating tailored engineering solutions for a particular site instead of generic solutions. And last but not the least, in all the solutions that we are providing, we are ensuring that we are economical and far better than the traditional solutions. Thanks a lot. I hope I am within time. But just to summarize, we are committed to reducing the carbon footprint, be more environmental friendly, and we have been doing a lot of innovations, benchmarking, testing to ensure that all our products, our solutions are aligned with the sustainable development goals. With that, a big thanks to you and all the dignitaries present here.
Thank you, Mr. Nanda. I invite Engineer Ravigaran Vaidya, member of the Finance Committee of Geotech Asia, to present a memento to Mr. N.K. Nanda from the McAfee.
Thank you.
McAfee is our diamond sponsor.
Yeah, quick correction, I am M.K. Panda. Thanks a lot.
Platinum sponsors of Geotech Asia are Rene Constructions, Monte Carlo and Afcoats. I request Ms. Dr. Amar Padak, Deputy General Manager and Head of Learning and Development at Monte Carlo Limited, to come forward for the presentation. So request you to kindly keep it brief and complete in 5 minutes. Thank you.
Sure. So very good afternoon and we are very thankful to Geotech team, including Professor Anil Joseph, Dr. G. Savasi and the entire team for providing this opportunity to represent Monte Carlo. I will take it quickly since I have very limited time, so I won't take much time. Show you one small video that will give you enough idea that what Monte Carlo does actually. So let me take you through the presentation. This is what we are into, so major 6 verticals we work into. So highways, building and factories, mining, water and irrigation, energy infrastructure. These are major verticals where we are operating as of now, and we have pan-India presence. These are our promoters. We have carrying 30 years of legacy now. We are a 30-year-old organization and having good presence across the nation, and we are proudly contributing in the development of our nation. So we are basically a diversified infrastructure development company, and we are headquartered in Ahmedabad. So, these are the major verticals, as I already mentioned, so I won't repeat. From vision to legacy, so we started our journey in 1995, and now after spending 30 years in this industry and experience, we are exploring more areas, more avenues to contribute. In that way, we are coming into renewable energies also. Till now, we are not in energy generation, but very soon we are coming into energy generation. So this is 30 years of legacy. You can quickly go through. So started in 1995 to 24. So you can see that how we evolve and how is our growth took place in this sector. This is our footprint across the nation. So we are operating in India. We are not, as of now, we have no overseas project, but in India we have almost, we have footprints across the nation. So we want to be the leading infrastructure organization that manage all stakeholders with sustainable growth through process, people and innovation. So this is our vision. And we actually follow this, and that's why we are now in our 30th year. Quickly I am moving. This is our core values. We call it action, and this action is aligned with our competencies and competency model and the entire value chain system. So for any organization, values are very important. So we have not opted these values, but we live these values.
Requested to conclude.
These are some of the projects quickly I am taking you through in highways.
Please conclude in 1 minute.
These are railway and metros. Yeah, sorry, somebody is saying something.
Here, hello.
Yeah.
Here, on the desk. Okay, please conclude. Please.
These are some of the major projects we have in verticals. Some award and recognitions which we have achieved in the recent past for our work, for our CSR initiatives. We continuously are gaining our presence across the industry. Here I am done with my presentation. Thanks for your patience to watch, and thank you organizing team for giving us this platform. Thank you so much.
Thank you, Dr. Pathak, for giving it crisp and short. I request D.G. Shahwashi, Joint Organizing Secretary of Geotech Asia 2025, to present a memento to Dr. Pathak. Monte Carlo is a platinum sponsor of Geotech Asia 2025. This conference has been a reality because of our benevolent sponsors. Thank you all. We have one more corporate presentation before we move on to the next keynote lecture. I invite Mr. Lakshmana Rao, General Manager, Engineer and Designs from AFCOS, to give the presentation.
Good morning everyone. We have a small corporate video, so we will play that. Let's watch it.
tracks of this gigantic superstructure across a 9-kilometer track could be the fastest in Indian metro construction history.
Averages in India, deepest metro station, having 30 meter of depth and involving 33 meter of acceleration, which is the deepest acceleration done so far for the metro project in India. As part of our program, we have also done India cross-track underwater tunneling, crossing the margin of the ocean. Plan and underwater tunneling and arrange all units in advance. That's a required for the underwater. Also, we design the tunnel movement such that in case of any accident or in case of any substance that arises inside the river, they can be converted into submarine. We are also executing the biggest ventilation shaft of the metro project, which is 44 meters deep.
Thank you so much.
Thank you, Mr. Rao. I invite Dr. A.P. Singh, the Organizing Secretary of Geotech Asia 2025, to present a memento to Mr. Lakshmana Rao, the General Manager of course. Our diamond sponsor is Mecca Ferry, platinum sponsors NA Constructions, Monte Carlo, and of course, the Organizing Committee of Geotech Asia 2025 plays on record our sincere gratitude to all our sponsors. Thank you. I now request the chair and co-chair to take over for our next keynote lecture. Thank you.
Friends, let me present and introduce this session's second keynote speaker, Professor Buddhima Indraprastha from University of Technology, Sydney. He will enlighten us on the theme of advanced geotechnical solutions for sustainable transportation infrastructure using waste material. Now I request our theme speaker to kindly go ahead.
Thank you, Chairman, for that introduction. First of all, thank you so much for the Indian Geotechnical Society and the organizers of the Geotech Asia for inviting me. It's a pleasure to be here. This is my third time in Goa, and it's always very interesting. Due to the brevity of time, I have cut down the presentation to have slides only relating to railways, and I've omitted the slides for roads. Simply because I don't have the time to go through everything. Given that there are many practicing engineers here, yesterday I took all the slides of constitutive modeling and equations out of my presentation. So hopefully this will be a live presentation with illustrating the concepts more than the actual analysis. If you look at this slide on the left-hand side of the picture, you will see the most populated part of Australia, which is our eastern coast between Brisbane and Melbourne, with the cities of Sydney, Wollongong and Canberra in the middle. Apart from being highly populated, this is the part of the ground that creates a lot of challenges for practicing engineers because of the abundance of highly compressible saturated clays and also we have a rocky terrain very often jointed rock. So the transport infrastructure is a challenge in this part because of the ports that are connecting Brisbane, Sydney, Melbourne. You need to have heavy haul trains as well as passenger trains. And in Australia, in this part of the world, there are commonly used tracks, so the heavy haul trains or the freight trains also have to use the same lines as the passenger trains. If you were to look at the right-hand side picture, you will see that after about 2010, the demand for railways and freights have almost exponentially, and that itself creates the problem of how the railways needed to be designed. If you look at the problems that people experience, especially in Australia, I mean, these problems will be common to other countries as well, including India. You will see railway tracks abandoned because the ballast is practically pulverized to small parts. There is not enough friction and they are in capacity. In the middle upper picture, you will see heavy erosion, substantial erosion of the substructure after flooding. On the right-hand side upper picture, you will see fluidized mud, which is coming from the subgrade soil. The soft estuarian clays, when the water content reaches the liquid limit, the soil becomes a fluid and comes up. On the left-hand bottom picture, you will see buckling of the rail. Now, this buckling of the rails did not occur because of high temperature. Temperature was only about 20 degrees that day. It's simply because the ballast needed to be maintained. When the ballast is not replenished, you lose the confining pressure of the track. And when you lose the confining pressure, the concrete sleepers tend to move under the movement of the heavy haul trains, and then you can get buckling. The middle picture at the bottom shows you a combination of many things leading to differential settlement, and on the right-hand side bottom picture you will see after heavy rainfall, if the substrate is not maintained, then there is poor drainage, then the cycle will continue, and you will get one or more of these kind of problems. This is flooding in South Australia. I've taken some of these pictures. You can see the amount, the catastrophic failures of the railways after extreme rainfall. So these need to be mitigated. Now, flooding in major cities is not uncommon in Australia. We just got to live with it. But the designers have to improve their design work in order to mitigate the post-inundation flooding damage that is caused to railways.
That's what
structure. So what I'm going to show you here is how waste like recycled rubber can be used to at least minimize the problems that you have seen from the slides that I presented earlier. So in Australia, we discard annually 2 times the population. About 50 million tires are being discarded annually in Australia. And they just accumulate in landfills and other areas, especially in mining sites. So what shall we do with these accumulated tire parts? So I came up with this idea about 15 to 20 years ago. There are different ways of using the recycled rubber tires and how we can to improve the foundation for roads and railways in particular. On the left-hand side, a tire cell which can be filled with waste materials, and then you can do the foundation of it, and I'll show you a picture of that later. In the middle picture you can see that railway ballast, about 10% of the particles can be mixed with rubber granulates. This is shredded rubber particles, so they are angular, they look like ballast particles. But the idea is that when you mix rubber with rock aggregates, you reduce the amount of attrition and therefore you reduce the amount of breakage. On the right hand picture, you can see that below the ballast layer, you have what we call the shock absorbing rubber sheet. So these are recycled rubber sheets coming from discarded materials from mining companies, and these rubber elements can absorb energy. So in all these 3 schemes that I'm showing here, the kinetic energy of the moving trains is absolutely substantial, you are talking about 70,000 plus tons, 350 carriages, moving at 80 kilometers per hour. You can calculate half mv square. That's the amount of kinetic energy that is dissipated onto the track. What these rubber elements do, they absorb that energy as a form of strain energy and then release that energy back to the track after the train has passed. As a result, you minimize the damage to the track elements. So here is a picture of assembling the rubber tires. You can see one of my PhD students actually putting the rubber tire cells together. You can see the rubber tire cells put together, and then these rubber tire cells get filled with base materials like slag, coal wash, crushed glass, bricks that are coming from demolished yards, and so on. Anything granular can be filled into these rubber tires, and then these rubber tires become your foundation on which you can build your road or the railway. So you can see on the right hand side bottom picture, the dynamic load actuator. This is 1-to-1 scale track simulator. You can assemble this structure and you can apply the real life loading onto this rubber tire assembly, and then you can calculate, you can measure the displacements, the stresses and the strains, and then you can do your design based on this particular form. Something which is very important with these rubber tires, as you can imagine. Try to compare this with geocells. Now, a lot of you know about geocells. What do geocells do? They provide confining pressure, but they don't absorb energy. So what this rubber tire assembly does, it does the same thing what the geocells can do, but at the same time, they are capable of absorbing the huge amount of energy that is dissipated in the track. As a result, you can reduce the sound, you can reduce vibration, you reduce the movement of the ballast, and you reduce the damage to the track elements. So here is the application in real life. So this is just the western part of Sydney, the area of Flora. You could see the Sydney trains, the companies bringing these rubber tires together, approximately similar sizes, and you bring them to the site, then you assemble them, then you instrument them as well, because we want to make sure that the circumferential strains are also measured, because if you don't measure the strains, that means the tires are not getting activated. So it is not just individual tires, but the rubber tire assembly acts like an integrated structure. So the instruments actually show you the pressure cells here as well as strain gauges that are going around the periphery. You can see from the right hand upper picture, you can see a pressure cell there, and that pressure cell actually measures the lateral pressure. In the same way, you can see the strain gauges here around that, which gives you the hoop stress that is measured around the rubber tire. Then of course you fill it up with waste materials. In this particular case, the ballast that you find here comes from a spoil tip, that is the discarded ballast from previously maintained tracks. You bring that ballast back and you fill these rubber tires, then you compact it. Now that compacted foundation becomes the, if you like, the foundation for the road or the railways that you can build on that compacted area. So this is a video of the construction. You can see it's been made in Shillora. You can see the filling of the rubber tire cells with waste materials. And the entire instrumentation works on solar power. And this is just a drone picture. And this is how the rubber tire construction is made. So two most important things coming from this. There are two main design elements that we need to consider under cyclic loading of railway tracks. The first one is the lateral displacement. If the ballast dilates a lot, then the track becomes unstable. So one way of reducing the dilation of the ballast is to increase the confining pressure and reduce the lateral displacement. And that's what these rubber tires do. The confining pressure is substantial. You can see from the shape of the rubber tires, obviously, and you can see from the left-hand side picture, the lateral displacement are reduced to a significant extent. The second most important parameter that you require in the railway track design is the resilient modulus. Resilient modulus, you can consider this as an analogy to the elastic modulus for small strain, but the resilient modulus is actually calculated after about 500,000 loading cycles. When the modulus, the dynamic modulus comes to a constant level, we call that the resilient modulus. And you can see that the resilient modulus has increased because of these infield rubber tires. As a result, you get a reduced settlement over the long term. So even though rubber is compressible material, at the beginning your railway track might feel a little bit more compressible. The drivers who go on this actually say at the beginning they felt that the track felt a little bit spongy, but very soon it becomes stiff when the rubber tires are activated. And then in the long term, your actual settlements of the track will be less than the tracks that are designed by the normal technical standards. So here is a simulation of mud pumping. Now, as you can see from the right hand upper corner picture, the subgrade soil or the estuarian clay will pump upwards when the soil becomes a fluid. Now, this is quite different to liquefaction. I want to make it very clear, and I don't use the word liquefaction. During my Menard lecture in 2017, I coined the word soil fluidization, deliberate to keep it out of the earthquake engineering domain. In earthquake engineering, liquefaction occurs essentially because the effective stresses become zero. But in soil fluidization, effective stress becoming zero is a consequence, it's not the cause. The cause is under vibration. The soil fabric changes. As a result, the moisture from below migrates upwards, and the top layer of the soil, the water content approaches the liquid limit. And when that happens, soil becomes a fluid. By definition, effective stress becomes zero after that. So please make note of that, that soil fluidization does not have the same concept as liquefaction. Now, this is a finite element analysis to show that the train is coming towards you, and when you see the red color that is coming up just below the track, that means the soil in that area is potentially going to fluidize. So, I have increased the loading on the train to create that fluidization. But of course, if you reduce the load, then you won't get the red one, you will get the other color. So now, in the next picture, I will show you the 3D analysis of this. And since some of you may be falling asleep, I will get you up with a little bit of music as well. So if I run this one, you will see the red color. You can see that on the top, the red color is absent. Okay, so what happens is, where the rubber tires are at the top, you don't get failure. But just below the rubber tires, you actually get the red color that is taking place. That means the rubber tires are protecting, you can see that from the picture here. The rubber tires protect the soil from being mud pumped, but below the rubber tires there is no protection, and therefore you can actually get mud pumping. So here is the conclusion of that analysis. You can see the finite element analysis of the rubber tire cells here in the middle, and that's the embankment, the railway embankment. And you can see here that the lateral displacements are substantially decreased by the use of infield rubber tires. Now, this is a very low cost operation. There are plenty of rubber tires started in India as well. Only thing you need to do is to bring them to a new track area or a track that has been made, fill it with waste materials, compact it, and then the track over that. So the ballast layer, the 300mm ballast layer will still be there, but it is actually built on top of this rubber tire foundation. So this is currently a patented technology, and if you have to use it, please do write to me, and I can waive the royalties and you can use it. So coming to the second part of the rubber tire mixtures, this is where we take part of the ballast and mix it with rubber granules. The idea of the rubber crumbs, you can see that the shapes are very similar to ballast themselves. You mix it with the actual ballast, and that is called rubber intermix ballast stratum. And then you can just put it onto the railway track and compact it the normal way. So if you do that, you will find that the breakage of the ballast is significantly reduced. So you only need about 5% to 10% rubber, and you can see that the breakage is substantially reduced irrespective of the confining pressure. Now normally on railway tracks, the confining pressure is around 30 kPa, but if you were to use geogrids and the rubber tire cells, then you can increase the confining pressure to about 60. So by mixing rubber granulates with the typical conventional ballast, the whole idea is to reduce the amount of breakage, as you can see from this diagram as well. So if you don't have any rubber granules, that is the typical Australian standard the track which will give these axial strains, and with the rubber tires with 15%, you have that curve. Not only will you reduce the amount of breakage, but you reduce the amount of axial strain. In other words, the settlement of the railway track is also substantially less. Now I'm going to show you, this is a video before I run it. On the left hand side, what you see is a typical ballast with no rubber or too much rubber. On the right hand side, you will see an optimal mix with about 10 to 15% rubber. And you can see how the mixing of rubber and its energy absorbing capacity leads to a reduction of noise and elimination of vibration. So if we run the first test, you can see the amount of noise and you can see the amount of vibration. Even the dynamic actuator seems unstable. Now that was a cubical triaxial box. Now if I run the right hand side, the loading is exactly the same, but you will find that there is hardly any vibration. Not even one particle of ballast is vibrating. So that is just with 10 to 15% rubber. So the optimum value is about 10 to 15% rubber. Now this is very easy to do in the field. You just bring the rubber granules to the site, you have the ballast, you mix it just by the railway, and then you put that and make the real railway track. And you don't need any extra skill. The mixing is done by the normal mixing machines, and then you lay the ballast with the rubber and just come back to the normal way. And as you can see on the right hand bottom picture, that is your completed track. So very simple techniques, anyone can do this. And it surprises me why all these scientists are doing. Now I'm coming to the third part of it. This is very important. This is about impact damage. Now, those of you who have observed railway wheels, not all of them are perfectly circular. I can assure you that. I mean, you can see the amount of corrugations on that, and that's a flat part of a railway wheel. And when these imperfections create impact, especially at relatively high speed, you get the hammer effect, because these imperfections plus the corrugations on the rail itself will give you an impact load. And it is that impact load that actually causes the damage to the railway elements. Now if you were to look at these measured impact loads, these are the stresses that are measured on a real railway track. As soon as a wheel like that crosses the point, you get that impact load. And that impact load can either fracture the concrete sleepers, or break the ballast, or damage the fasteners. So in order to eliminate this impact damage, you can actually have recycled rubber sheets that can be put underneath your ballast layer. Before doing this is just a discrete element model. to look at the effect of particle sizes and shape. I think this morning Professor Madhavi Lata gave a very elegant presentation on the effect of particle sizes and shape. And this is very simple. The particle sizes and shapes are created with the actual geometric coordinates, and then you can mix these particle sizes with a discrete element model, and then you can calibrate with the laboratory work, as you can see from this. I mean, you won't get an exact fit because you will never get perfect shapes as you are in the for real ballast, but it's quite close. You can see the impact forces, the P1 forces and the P2 forces are quite close, and that's for with a rubber, without a rubber mat, and that with a rubber mat. As soon as you have a rubber mat, you will find that the impact force P1 is considerably less. It's reduced by about 40%. So the discrete element method can actually calculate what type of loading and what type of impact forces can be expected, and how you can control that by using these rubber sheets. So you can see here in a part of Sydney, just in the western part of Sydney again, where recycled rubber sheets are put on the compacted subgrade. So you will have the ballast compacted on these recycled rubber sheets. So that's just a schematic diagram of it. You can see the ballast layer and you can see the rubber sheets. So these rubber sheets are actually made from discarded conveyor belts. You get kilometers and kilometers of rolls of discarded conveyor belts thrown out by mineral processing companies and mining companies. And they are slightly damaged, but they can still be used for the purpose that is here. Now, on the right-hand side picture, I'm going to show a laboratory simulation of the impact load. Calculate the P1 impact load from the discrete element model, and then you apply the computer model to the dynamic actuator, that value of P1, and that is a sample of ballast that goes to the triaxial equipment later on. But with this application of the load, of the impact load, you can then measure how much the particle size distribution has changed, and therefore calculate the damage based on that impact load. So if you can run that video, you can see the hammer falling and creating the impact. You can see the deformation of the sample there itself. And then you take this sample back, you recalculate the particle size distribution curve by sieving, and the difference between the original and the final particle size distribution gives you the breakage index. So here is a summary of how these rubber sheets work. The best result that you get from these rubber sheets is if you're on a concrete bridge deck. On a concrete bridge deck, the reaction forces are very large, so the ballast breakage is expected to be significant. But if you're on a soft soil, then the rubber sheets don't really do much, simply because the soft soil itself is ductile, so the soft soil can itself absorb quite a bit of the energy. As long as it doesn't fail, the soft soil itself is an energy reservoir. So the best application of the rubber sheets as a shock absorbing or impact damping element is either on a concrete bridge deck or the track is made on a rocky road. So then you can use these rubber sheets very effectively. I'm not going to go to the details of it. Constitutive models have been produced, how these rubber elements have been used, because in design, you can't do a design by looking at pictures, you need equations, you need finite element models, and we have developed these energy absorbing details by looking at two types of energy. When you are looking at the granular materials, particles can slide over each other, or the particles can roll and break. So there are two types of energy. The energy that goes to sliding of particles without breaking, and then the energy required to actually physically break the particles. So if you add these two together, that gives you the total energy. Now, when you have a triaxial equipment, you can measure the dilation of a granular material. You can calculate from the strain energy the actual energy that is experimentally determined. then you plot the actual energy dissipation calculated in the laboratory on the horizontal axis, the equation, what you predict from this equation on the vertical axis, that is the 45-degree line, and you can see that it's a pretty good fit. So the calibration of these equations are done, and the parameters A, B, and C are empirical parameters, and by fitting them onto the 45-degree line, you can back calculate the A, B, C values that are required for a given rock material. So it doesn't have to be one type of ballast, you can take any type of ballast, and you can use this technique and calculate the energy absorbing capacity. And then these equations can then be put into the finite element stiffness matrix, because the stiffness matrix, as you know, can be assembled by an energy approach as well, the virtual energy approach, and these equations are then added on to the normal conventional scaling equations. And then the finite element method will take these equations and calculate the displacements and the strains. So here is some pictures of these applications in real life. This is area called Singleton, which is very close to Newcastle, north of Sydney, and you can see the rubber sheets being laid. You can see extremely bad corrugation on this railway track here. So you obviously get impact on this. So you can see the rubber sheets being laid. Pressure cells are being put on this concrete bridge deck, because this is where the biggest breakage will take place. And the pressure cells will actually tell you how much stress is going through to these rubber sheets. And here you can see the rubber sheets being laid in this bridge deck, and then the ballast is being put, and the track is completed after that. So this is just a summary of the ballast breakage assessment. As I said earlier, the impact damage, to minimize the impact damage, the effectiveness is greatest when the subgrade is very stiff. So if the subgrade is wrong, or if it's a concrete bridge deck, you can expect the ballast particles to be crushed very quickly because of the high reaction. So you will see that on a concrete bridge deck here, the breakage is much less. So if you are here, that is the original track, you can see that for both rock and soil, the particle breakage will still be reduced to some extent using these rubber elements, but the best effect is if you are on a concrete bridge. So now in Australia, it's almost accepted that when you are on a concrete bridge deck, you will simply not put the ballast right on the concrete bridge deck. You will always use this, and we call them shock mats, and you can easily make this with recycled rubber, so it's a very cost-effective process. So coming to the conclusions, the rubber tire track increases the confining pressure and reduces particle movement and breakage at train speed. By mixing rubber granulates with the conventional ballast, you reduce the attrition between the particles, and as a result, you reduce the breakage, and when the particles don't break, they remain large even after a long time. As a result, you reduce the settlement of the track. You already know that when the particles start breaking, they compact more and the settlements are larger. So if you prevent the particles from breaking, you have great amount of friction and you have less settlement of your railway tracks. Recycled rubber energy absorbing mats are excellent as impact damage and ballast breakage prevention, and these are cost effective if you can make them with recycled materials. It is very important that all this academic work, the finite element models, the discrete element models, there are a lot of complicated equations, but for practicing engineers, in my experience, I work with practicing engineers all the time. In fact, I have more projects with practicing engineers than actual academic theoretical engineers. And what I've always learned is that if you want something to develop at a university, and if you want practicing engineers to adopt them quickly, don't make them constitutive models. Just demonstrate that in the field, that they actually work. So that's condition monitoring via field work, and that is what we have seen from these slides. The computational FEM and DA models are important for designing, because as I said earlier, your design codes need to be refreshed, they need to be rejuvenated, because some of these design codes are pretty old, but with the modern numerical models, you can actually capture these concepts, such as the energy absorbing models, and then you can redo this railway track design, capturing particle breakage and the confining pressure, as I explained. To end my presentation, I would like to acknowledge the Australian Research Council for supporting these projects over the last 20-25 years. Fantastic PhD students and research associates who have been doing the hard work. And of course, universities don't own railways and roads. So I have to thank the industry partners, not only supporting these projects, but actually taking the outcomes, adopting them, and then enjoying the modern designs as we have now in Australia. And finally, the UTS Transport Research Centre that I lead as its director, which is the largest transport research centre in the country at the moment. And you can see my second family up there with all the top PhD students and the research fellows. And if you didn't really understand some of the concepts which I just talked about, the new book on waste materials utilization for transport infrastructure is just out. So you can purchase this book. There's a student edition and also there's an online, the digital edition that you can download, which is very cost effective. I still have about 45 seconds left, but that's fine. Thank you very much.
Thank you, sir. I invite the chair and co-chair of this session to present a memento to Professor Pudima Indraratna from the University of Technology, Sydney, as a token of our gratitude. Thank you, sirs. And with that, we move to the last keynote lecture of plenary session 4. Over to the chair and co-chair.
So we invite the last keynote speaker of the session, Professor Lacy Lloyd. He will be presenting on biocementation. Now please adjust the time, please. Is the keynote speaker? Please, sir.
Good morning, ladies and gentlemen, dear colleagues. It's a very great pleasure to be with you here today. I'd like first of all to thank the organizers for this kind invitation. The talk that I selected for this morning is dealing with biocementation. I would like to take you over a journey of 15 years development to show you from where more or less we started and where we are together today in this area. So 15 years in 30 minutes, you can understand easily that I will remain at the high level in many concepts, but basically I would like really to share with you what were our steps. So basically just to start with, so what is biocementation? So it's a way to cement soil, strengthen it, but it's a way that we try to do it naturally by having calcite precipitating inside our porous media through the biological process. Basically, if you have a soil from one side, you have measure that you are able to create your structure of calcite. So our goal basically is to put this calcite inside the soil to have it cemented and dissipate, and this is what we will call biocement material. So why do we need this? Why is it important, I think, for our field? Actually, all of you here in the room, I'm sure, are familiar with the traditional miners. So matter whether cement that you inject, lime that you use, resin, all those binders, they have a major issue. That is an environmental issue. Those, our conventional soil improvement techniques, they pollute water as you know it. They have issues with grafting wastes, and even the production, the cement, create major CO2 emissions issues. So we need to come with something different in our field. And this is what is initiated since almost, I would say, 10 years at least, by having this microbial-induced calcite precipitation process that we talk about. Why is it important for us? Because it's a natural process, it's completely environmentally friendly, very neutral to nature, and highly efficient, which is also very important. Because if we come with a new technology, technology should be efficient, should be also from financial cost effective. So this is also an item that I will cover. So, and then you can apply it to all type of conventional reinforcements that you are familiar with. So basically, to summarize this introduction, the idea here is that with the liquid agent, because we will use liquid with the viscosity of water, we would like to turn, let's say it simple way, sand in a rock in a fast way, long-lasting, almost forever, and by promoting also safer and more sustainable work. So the history of this technology is not that old. So we started, there were some groups, let's say, our first paper was in 2009. Since then we see the growth in terms of scientific production, the community is really impressive. And I think it's almost the most dynamic field in terms of journal papers next years. 2 years ago, we were almost more than 400 journal papers. I would like to mention one of the first publications that we did, this book that it was a technique symposium in print in 2013. At that time, our community was considering this field as an exotic. But what I will show you right now is all the parts that we did to enter the market, to provide a product that I use in my practice. Also, I would like to mention the process was not that easy. The steps were very difficult. And here I would like to highlight and to thank my colleague, friend, Inishi Sota, when we were having a hard time at the beginning of 2010, 2011 to really rely on experimental tools, and he was very supportive. Thank you very much, Inishi. So, I will talk briefly about what are the chemical physical processes, because it's important that we understand the processes. So as soon as we understand processes and we talk about how we model them, we have to be able to design the progress of the fluid inside the porous material. We have to be able then to design the resistance of the mechanics that we are getting. And then we conclude by showing how we enter the market with a new product. So, chemically speaking, what we are talking about is a simple process where we mix urea with water. We do this to get ammonium and carbonate. This is what's happened in nature to get rocks actually from sand. Sandstone is like this. The only thing we make the process faster by using bacteria as a fertilizer. So we increase the process almost 10% power. If this carbonate that you get, you mix it to calcium, you get your calcite, calcium carbonate. This is what you see actually here inside water, is simply calcium carbonate forming in water. Basically what we will do, in our case, we will extract this ammonium to put it aside. Either we will make product from it, that I will not discuss that much today, but what we will work on is this process. So the goal now is that what you see here inside tubes of water, we would like to have it happening in the soil. So we would like to be able to inject porous material and to ensure that we have distributed development of the calcite inside our process. And this is what we can get if we do it. So this is an X-ray CT micro analysis of cross sections, horizontal and vertical. And what you see here in red are calcium carbonate distributed inside the sample, and in blue are our solid grained particles. So we see that the distribution is rather uniformly obtained, which is a good sign. So now if we compare with the existing materials, binders, that you can get in the market, so basically we use those type of materials, either cement, bentonite styrene, can use cement, can use microfine cement. And if you consider this kind of porosity area here, The maximum that you can enter in fine grained materials, let's say it's around 10 micrometer, you cannot inject lower than that. Using biocement solution is a liquid. So you can inject liquid so that you can inject any type of size almost. And if you even inject it with your bacteria, because you would like to have the process happening on the ground, in that case the size of our bacteria are, let's say, 5 micron maximum. So it means that you can enter really fine grained salts. The advantage of our solution, our approach, is that when it is cemented, so when it transformed in a solid particle, this is what you see here, this is the average diameter that you get for your solid matrix with respect to the distance of injection. So you can get something almost of 70 micrometer of size. So you can have something almost double of this size of conventional cement inside your material that you were able to inject. The other aspect that is important to have in mind is in terms of change of porosity or permeability rather. So here we go one step further in terms of size, and when we look to how our calcite is put inside our solid material, you see we attach to the grains, but basically we don't change that much the permeability. Actually, climatic permeability will change just by 1 order of magnitude. So we are not creating impermeabilization of the ground with this injection. So if we compare now the techniques of soil reinforcement that you are familiar with, the biocementation is able to cover from some fine-grained soils or some clays here until the ground. And it works almost in all conditions that we are familiar with. There is no issues. So as soon as we know about the processes, now let's look how we can model, design, control when we inject this solution in the ground. So to do that, we have to deal with tools, mathematical tools. So sorry for the equations that we see now, but are really needed to design any project. So our porous materials will be described in this way. So you have phases that are the minerals, calcite, or water, liquid, or if it's partially saturated, you can have different fluids there. But usually in mechanics of porous material, we can handle the same things in terms of species, which is better from computing perspective. So we can have those different species that you see here. So I'm not going to details, but we describe this separately because this will allow us later on to write the correct and right mechanics for it. And then we look at what are the physical processes, where there is mechanics, stress strain, hydraulic, Darcy law, biological and chemical processes that I was showing before. The point is that all those processes will interact with each other, so we have to express that also in our equations. So some equations to deal with that. So as I said, we describe the things in terms of species. So we simply express conservation of quantities for each of those species, which is the reality of the things. So the species that we are having are bacteria, are ammonium, are our calcium carbonate, and urea, plus the fluid, of course. There is one equation that applies to all of them, because all of them are fluids. Including solid matrix, it has its own mass balance equation. So we apply simply this mass balance equation, that this is change in time, this is convection there, here we have this fraction, and the diffusion and the two source steps. We apply this equation to all of them. And I was saying before, there are two ways to have the process. Either the reaction will happen in the ground with the bacteria. So in that case, you need to express the reaction of it that we express with this mathematical equation, or you do everything outside the ground in a bioreactor. In that case, you need just those equations. You don't solve this one. So if you do it in bioreactor, this is what we call it hydrolysis. So you have the precipitation rate that you express this equation. From this term of the precipitation rate, you introduce it into change of porosity. If you change of porosity, change of porosity will give you change in permeability, and to this you add diffusion and dissolution. So, and this is last set of equations, you will not see more today. Just to be able to analyze your system, you have to solve those equations. Depends on the type of injection that you do, you either absorb them, all of them, or just those that are taken here. So you have conservation of the mass of the fluid, those elements here, precipitation, and you have equilibrium. So as soon as we get something like that, we have to validate it. So to validate it, we have to run a large number of experiments. So we designed this, say, geomechanical lab or something like this, this system where we are able to control all the boundary conditions. We are able to control the hydraulics, the mechanics, the injection, and so on. So there are two basins of 150 cubic meters of soil. One we will use as a reference basin each time, and one the injection one. They are independent. We have the drains that you see here. We have 18 of them, and we have 16 of injection tubes. Here you see the size of our tubing. And then we were able to run a large amount of experiment that allow us really to check the validity of our model, to improve it, and so on. So basically, in each type of experiment, we look, for instance, from mechanical perspective, we can do dynamic pilometer test. We look to the shear stress of it. So blue, you see, it's rather low values, and treated material at different depths, different cross sections, and the more it's yellow, the higher it is. So let me show you a real example. For instance, in this case, we are having also statistically, it's important for us to have things well reproduced. We have 29 tested and treated sand. On the right side, 42 tests in treated sand, injected sand. Different walls, we have 8 of them, injection walls, and all the small points are measurement points. So we get different ones. So for instance, if we look to the tip resistance, we are in tube number 1 here, at 2 different distances. This is before injecting our ground. Let's say it's average value of resistance 0.5 megapascal. After injection, we move to 2 to 3, almost to 4 megapascal of strength in the ground. This is vertically distributed, different walls, different tubes. So this is the type of things that we get from this experiment. And then we can look also at technology for injection. For instance, if you'd like to have it uniformly distributed, we can use deep pipe. So in that case, you see we have uniformly distributed improvement of strength at the distance of 50 centimeters from the injection point, moving from, let's say, 1 megapascal to 4 megapascal resistance. And if you like really in some points to have a very strong increase of strength, like for stabilization of slope, when we have layer that you like to stabilize, for instance, if you use what we call two-bound shed pipe, we can even reach 20 megapascal of strength in identified points. So as soon as we have this, just to show you how it looks like, in the experiment, when we remove the non-affected areas of the sand, this is the type of cemented areas that we have. So with this, we were able to validate our design tools. We are able to say what, where, when, how much of quantities are produced in the ground in the system. With this, we can reproduce, for instance, the experiment that I was showing you before, where we have 8 injection points. We are behavior. I will not talk that much about the cyclic component. We have cyclic component in it, of course. So we started by doing conventional tests on cement materials at different calcite amount. So this is UCS, this is the modulus. As you can see, we have an increase of the resistance with the increase of the amount of calcite, but this is not going in infinity. We have a kind of elliptical shape of it, or exponential shape of it, so at a given time we reach limit that we cannot improve anymore the resistance, but we have this increase of resistance for different type of sands. In this case, we have 3 of them that are tested. From here, we came with the concept that depending on the amount of calcite that we put in the ground, we can treat different type of problems. So if we are dealing with liquefaction or erosion protection, we need very limited amount of calcite, so let's say between 2 and 3 of calcium carbonate is enough to treat this. Indeed, with increasing bearing capacity, you need a little bit more and so on. So this was the starting point for that, and then we tried to do also conventional testing, technical testing. So we did odometric test at different values of precipitate of calcite of different materials. As we can see, we found conventional techniques of cemented soils in general. You have an increase of the rigidity and you have an increase of pre-consolidation stress with the amount of calcite. And of course, if you have an increase of pre-consolidation stress, look now from the other side of the shear strength. So if you compare, here are three triaxial tests, three confining stresses. The first results are untreated material, and here you have treated materials. Different colors are medium sand and fine sand materials. So you increase the peak because you increase your pre-consolidation stress. Then you come back to your state at the end. And for instance, if we compare an untreated sand of 0 kPa with the treatment of 8 megapascal, in this case we are reaching something like 350 kilopascal. So it shows you the increase in cohesion in terms, but also we have in terms of increase of friction at the peak that you can see in some numbers. If you introduce this in the shear plane, so in the volumetric plane, of course, we introduce dilatancy, as you can expect it. So now we are having materials that are dilatant material, and then we come back to our conventional critics. So we try to understand what is the reason for those processes. So we went very deep, let's say, to the microfluidic level. So we went very deep. We worked with chips of this size, 5 by 3 centimeters, where we generate elements of 1 meter length. So we represent 1 meter length, that's very small chip with different grain size distributions, but same porosity. Try also to understand. So those two elements that you see here are both of them having porosity of 0.5, 1 meter length, and in real time we evaluate the dissipation of the solution and the precipitate inside the bottle. So this is our PDMS sheet. So we inject with syringe pump first our bacteria solution from this side, follow the things happening. As I mentioned, it's 3 millimeter wide. 7 by 5 centimeter size of it, and we inject the other solutions from on the side the solution, and we look what's happening. So I will start with the left side because it's the homogenized way of distributing porosity. So you see here generating this calcite happening in different points. Then we come back to it. You see it better when we have heterogeneous material, which is more like a natural material. So what we see basically is that we have two types of contacts are created, two types of rows that this calcite is playing in the ground, in the soil. So the first type is that it creates bonds between the grains. You can see here that we call it effective bonds, because this is created glue between the grains. The other type is that they are put on the surface of the grains, but they are not making them in contact. So they are just densifying them. So from this process, now if we go now to the X-ray, we analyze the observation in this way. From one side, we have densification. All those elements that are on the grain, this is blue calcite elements, solid grain on the grain, but they are not making the grain tincture to each other. From the other side, we have cementation, this glue that is now joining the grains together. And basically now the exercise is rather easy because we have just to introduce those two elements in a constitutive way. In our case, we started with the concept model that I'm familiar with since time when I was at the Conservatoire in Paris. This usual model that is biocementation, but you can apply this to any model from Campney family of models. So well, basically what you have an elastic nonlinear part, which is modulus and bulk modulus. You have the deviatoric here limit represented by its size by the reconsolidation stress. Then you can have something else not that important. And basically we modify those three parameters to take into account of this bonding and densification. So from densification, so each time we have to do it for the elastic plastic component. So we have the bioelastic part. So basically, bulk modulus and shear modulus, we have introduced a coefficient here, representing densification that is related to the density of the calcite and the mass of calcite in the soil. From the plastic part is very conventional classification of Campini type of models. You are increasing your reconsolidation stress, you are changing your specific volume. And this you do it by introducing this term here, that is a densification wire. So you have now an apparent reconsolidation stress with respect to the initial reconsolidation. Then you do the same exercise for bonding. So for bonding, now it's in terms of shear modulus. So we use the shear velocity, wave velocity as an element to define this bonding coefficient that we put here again as a coefficient for shear modulus. And for the plasticity part, we will act like for destructuration of agriculture soils or any type of clay that are structural clay, which basically, if you have an increase of your reconsolidation stress, that makes you going to a value that is higher than your initial reconsolidation stress, and then the more you shear the material, then the more you tend to come back to your initial normally consolidated line. So this debonding somehow, or destructuring of the process, so we induce with this coefficient here, exactly as people are doing with the destructuration of structural elements. So with this last item is related to the cyclic modeling for liquefaction aspects that I will not discuss that much, but just to show in terms of G-gamma curves that you are familiar with, our new shape of the G-gamma curve will be like this, showing that you need more energy to reach liquefaction for those type of materials. So if you combine all those things together, what basically you are getting is that if this is your untreated material with its Yen limit here, when you treat your material, you present what we have seen before in the experimental results, and I will just show here one case with back analysis of two experimental results from the literature, where when you put those ingredients in your model, you will get an increase of strength in terms of peak, then you come back to your critical state, and you have same thing, latency that is. So from this, we said how we can move to the market, how we can make from this real product using on daily basis on the market. So we started first by patenting what we developed. So here I'm showing you three among our patents. The first one is a system for ground consolidation that I was showing you before. The second one is how to produce such solutions that is nitrogen-containing species-free solution. Third one, how to combine our solution with geostat. So those among the things, and I will focus today just on one of our products, the VS1. And we developed also three exclusive microorganisms to have the process happening in a more efficient way. So these are the steps for the thing. So we have manufacturing regions, so either we manufacture in the basic space or we have wide manufacturing systems. When we do that, we produce our bacteria, we have growth by giving it nutriment, so they are the urea. We have carbonate production with known stability, quality-free nitrogen, and we combine the things on site in bioreactor. Of course, all this process is following all the regulations in terms of ISO norms or European norms, so everything is functioning professional way. So this is how it looks like on site. So we have our two solutions coming from the bioreactor. This is of course microkernel excavation. So the solution I said is a liquid solution, so you don't need too much pressure. So it's really 1 bar of injection that you apply, and basically this is what you get. You start from a material like this before injection, and you get solidified material. When it comes to slope stabilization, I was mentioning here before, usually we have this layer that is a weak layer, so you don't need to strengthen the whole ground, but just we focus on the area where we have failure line. So we see here is this project where this is tip resistance before injection, and here we target to enhance strength at 1 meter depth. So you see here we reach almost 30 megapascal. We can do it also for other conditions. This is sensible if stabilization. Here we inject horizontally. This time, this is the bioreactor that I was mentioning, where we put the solutions together, we inject them with the different pochettes that I was showing before, and basically what you can see is that this is before injection, this is the seismic wave velocity. Blue, as I mentioned before, it's a very, very bad material, and after injection we are reaching something like 2,500 meters of meter per second. Those red zones, which is the shear velocity of a rock. So this is what you can get in those things. Before concluding, what matters for me is really that this technology be really used by practitioners on a daily basis. So I would like to show you a short video, 1 minute video, with one of our engineers in one of our projects explaining to other engineers with his word how this technology matters. Just 1 minute video. Hope that you can hear it. Can have sound. We have the sound.
Consolidate the weathered rocks in front of the buttresses of the retaining. An innovative and environmentally friendly solution, biocementation. So today on this site, the goal is to reinforce the soil at the base of the buttresses. What we do is drill down until we reach the hard, unweathered rock, which is about 2 to 3 meters deep. Then, as we pull back up, we inject our biocementation liquid, which will seep in through the soil's porosity and spread out. And under the effect of our microorganisms, calcite crystals will precipitate, and thus reinforce the soil by providing cohesion, since these calcite crystals will bind the soil grains together, fill in the cracks and strengthen, consolidate this soil, this weathered rock.
So that what matters, I would say, is that to be able to have language for practitioner engineers on a daily basis to talk to others. But also what matters is that to have recognition from the practice, from the people, from the users. So last week in London, we were the Geotech Awards for ground engineering. It's a kind of the Oscars in our field, that's what I'm familiar with. And we got an award in competition with the largest companies in the field, McDonald, Page, Addison, all of them were competing for this, for innovative material solution supply. I would like to read what their evolution was. The judges said Medisol presented a highly innovative product that addresses a known area that must be addressed by density if we are to achieve sustainable target. Judges were impressed by the scalability and the use of standard readily available plants and equipment. The panel realized that Medisol had achieved an incredibly difficult to do. The evidence of real-life application was very impressive. But not only that, we got 2 awards. We were the only company who got 2 awards last week. We got also the award for erosion defense. Just to say, the judges prized Medisol submission demonstrating 85% CO2 reduction, circular economy via ammonium sulfate use, and zero ecological impact. This is a fully scalable, ammonia-free biocement with no capex barrier, strong Okay, but you can imagine we were very impressed. So we were very impressed by getting those 2 awards. And to conclude, so what I was trying to show you is that how we transform what is intended to transform scientific discoveries in market solutions. So with this product, what we do and what are the characteristics of this solution, it works with all types of soils, from clays to gravels, can be applied via injection or with traditional equipment for mitigation of liquefaction potential.
We can apply it via mixing or like a short plate for application like erosion was mentioned before, but in other situations. Can also serve for excavation, demolition, waste valorization. Thank you very much for your attention.
Thank you, Professor Leloy. And to present a memento to the speaker, I invite the chair and the co-chair. Thank you, sirs. And now to present the mementos to the chair and co-chair of this session, I invite Engineer Renikaran Vaidya, member of the Finance Committee of Geotech Asia 2025. We express our gratitude to the chair and co-chair for keeping this plenary session 4 on time.
Co-chair. Yes. No, I'm doing it.
Thank you, everyone. Post-lunch, we have panel sessions from post-lunch, we have panel session from 2 p.m. to 3:30 p.m. And from 4 to 5, we have a panel discussion on advances in geotechnical engineering across Asia, featuring the presidents of Asian Geotechnical Societies. And from 5 to 6 p.m., we have the Asian Awards ceremony. Geotech Asia 2025 is thankful to all the sponsors. Our title sponsors were Sani Sankya Group and J. Kumar, Diamond sponsor McFerry, Platinum sponsor NK Constructions, Monte Carlo, and of course, Gold sponsor Keller, Savi Infrastructures, TechFab India, Garware, Sani, Pioneer Foundation Engineers Private Limited, Hawaii Group of Institutions, Megha Engineering and Infrastructures Limited, and silver sponsors were ITD Cementation India Limited, Strata, Ferroconcrete Construction Private Limited, PRD, SMC Sohams, and Green Sustainability. Our lunch break will be till 2 p.m. and post-lunch we have the panel sessions, which will start sharp at 2 p.m. Thank you all.
Entonces, mira, te dañaba.